Alright, are there any questions from last time? So now we have already seen how to do genetic regulatory network modeling, right? One possible approach would be to use COD to find out predictive relationships between genes and then put all that information together, come up with genetic regulatory networks, right? But what do you want to do with that? I mean, once you have genetic regulatory networks, you can use them for modeling the behavior of the system, right? And our goal, if we are looking at cancer therapy, might be to move the genetic regulatory network from a state that is known to be bad to a good one, okay, by doing some kind of intervention, right? So this chapter is going to deal with intervention, right? So the ultimate objective of genetic regulatory network modeling is to use the network to design different approaches for affecting network dynamics in such a way as to avoid undesirable phenotypes, for example, cancer, okay? Or many of you are in agri-life, okay? The undesirable phenotype would be the plant is heavily dependent on water, okay? You want it to use less water, okay? So the pragmatic manifestation of this goal is the development of therapies based on the disruption or mitigation of aberrant gene function contributing to the pathology of a disease. So if you're looking at cancer, mitigation would be accomplished by the use of drugs to act on the gene products. But then you would like to know, which drug should you use, right? Which is the one that is going to give you the biggest bang for the buck, right? So engineering therapeutic tools involves synthesizing nonlinear dynamical networks, analyzing these networks to characterize gene regulation, and then to develop intervention strategies to modify the dynamical behavior. Okay, so this is like a control problem, right? You want the system to behave in a particular way, right? So you want the gene regulatory network to evolve towards, good states. Right? Of course, you have to characterize that. Now, so we talked already about probabilistic Boolean networks, and so on, right? So if you have changes in network connectivity, let's say there is some oncogene that turns on, okay, it's permanently at 1, okay? Even if the stimulus is not there, okay? So in that case, you could have steady state behavior that is associated with the formation of tumors, tumorigenesis, and this is likely to lead to a cancerous phenotype unless corrective therapeutic intervention is applied, right? Now, we have considered, you could use different frameworks for, carrying out intervention in gene regulatory networks. You can use different kinds of models. The ones we used and the ones which are most convenient are the probabilistic Boolean networks, right? Because these, as I'm going to show you later, these can be modeled as Markov chains, okay? And there is a big literature that is available about intervention in Markov chains, okay? So intervention studies using PBNs have used 3 different approaches. The first approach would be to reset the state of the PBN to a more desirable initial state and let the network evolve from there. So the system has ended up in a bad state, okay? You can force that state to some other good state, and let the system evolve from there. So you don't change the wiring of the network at all, right? The second one would be changing the steady state behavior of the network by minimally altering its rule-based structure. So there you change the wiring of the network a little bit so that it now has good looking attractors or basins of attraction and so on. Okay, that's another approach. And the third one would be to use external control variables that alter the transition probabilities of the network, right? Because then this becomes what is called a controlled Markov chain or a Markov decision process, right? And there is a big literature dealing with that. In fact, that is used in many different areas in controls and in communications, right? Like controlling queues and things like that, okay? So these things were done a little bit before I got into the area. This is the one where we did like the first paper on putting external control. But again, I have to re-emphasize that, if the actual system fits the model that we have, right, then only these things will work and work really well, okay? Until you get them to fit, it is still just theory, right? So translating it into applications, that is quite a big jump, and we are still working on that. So in this particular chapter, we are going to focus on the first 2 approaches, okay, where you're given a gene regulatory network, right? Let's say probabilistic Boolean network, and you want to do like a one-time change. You want to force one gene from 1 to 0, that'll move the state somewhere else, and you hope you did a good thing, right? Another one would be like if you look at the truth table for the probabilistic Boolean network, you'll go and change some of the entries in that table, okay? That will change the underlying wiring of the network, and hopefully that's going to give you good behavior. So the other one where you use optimal control theory, that one we'll talk about in the next chapter. So in this chapter we discuss intervention results obtained using the first 2 approaches, right? The results obtained using the third approach and their variants will be discussed in the next chapter. Now, once you're given a PBN or probabilistic Boolean network, the transition from one state to the next takes place in accordance with certain transition probabilities and their dynamics, right? So there is a probability, and I mean, if you look at the original PBN papers, they fully outline the method that can be used in going from these rule-based structures, all right, to the transition probabilities, all right. But once you have these transition probabilities, it's a network that has certain probability of transitioning from one state to the other, okay. So then it becomes basically a homogeneous Markov chain, right, with a finite state space, right, and you can use, all kinds of results that are available from many, many years ago, 30, 40, 50 years ago, right. So let's see how the PBN could be put in the form of a Markov chain, right. So to characterize the Markov chain that is associated with and we'll first look at instantaneously random PBN because that's easy. This is the kind of PBN where the network can potentially change at every time point. At every time point you're picking a particular network with a certain probability, it's going one time step, then you're changing the network, right? So how do you, go from these two Markov chains, all right? So let's first start with Boolean networks because in the case of a Boolean network, you don't have to do any network switching. It's a fixed network, all right? Now, if you look at a Boolean network, let's say with n genes, all right, then the state vector at time step k is basically an n-digit binary number, right? And you can get its decimal equivalent just by using this formula, right? So if the state vector is a binary number of length n, okay, you are going to have these expression patterns, 0, 0, all zeros, all the way up to all ones, okay? There will be 2 to the power of n of them, right? And you can, instead of working with these binary numbers, all right, what you could do is you could replace them by the decimal equivalent because it's a one-to-one map, right? Nothing changes, right? So to do that, you basically, corresponding to each pattern, you calculate the corresponding decimal number, add 1 to it because you want it not to go from 0 to 2 to the power of n minus 1. You want it to go from 1 to 2 to the power of n, all right? So as xk ranges from all zeros to all ones, zk takes on all values from 1 to 2 to the power of n. Okay. Now clearly, and again, if there are any questions, stop me and ask me, right? If something is not clear. But I think, you guys are people with strong quantitative skills, so this should be quite straightforward. So the mapping from xk to zk is 1-to-1 and onto, and therefore it is invertible. So instead of using the binary representation xk for the state vector, you could equivalently work with the decimal representation zk, for which the state space now is basically the decimal numbers 1, 2, 3 up to 2 to the power of n. Okay. Now each of these guys, okay, you can go a step further. Each of these fellows, I can represent them by a 2 to the power of n dimensional vector. Okay. For 1, it's going to be a first in the first element and then zeros everywhere else. Then for 2, it's going to be a 1 in the second element, zeros everywhere else, and so on. Okay. So I can recommend. I mean, it's a much higher dimensional representation. Okay, because we had n genes, now we are looking at 2 to the power of n dimensional vectors. Right. So each zk can be uniquely represented by a basis vector. For example, if zk is 1, then it's 1 in the first component, zeros everywhere else. Right. Now the evolution of this dynamic system, right, you can represent it using this matrix A because, I mean, the total state space is basically 2 to the power of n vectors like this, 2 to the power of n dimensional vectors. Okay, so all you need to figure out how the system is evolving is the map from each of these to what is going to happen at the next time point, right? And so you have an equation of this form, right, where wk is a row vector, wk plus 1 is the row vector at the next time step, and this matrix A is going to tell you, you pick a vector, a basis vector, okay, which basis vector it is going to map into, right? So, and A is going to be a 2 to the power of n by 2 to the power of n matrix, having only one non-zero entry equal to 1 in each row, right? Because it's going to pick up only one of the vectors, right, out of the 2 to the power of n vectors, right? No problems with that. Now this can be generalized because, see, this is for the Boolean network, all right? In the case of the Boolean network, all right, each state is occupied with a probability of 1, okay? So you are either in this, you are either in the first state or in the second state, and that's why you have vectors like this, 1 and all zeros, okay? Then 0, 1, all zeros, 0, 0, 1, all zeros, okay? But in the case of a probabilistic Boolean network, it's going to be a bunch of numbers that sum up to 1, okay? And that will become the transition probability matrix of the Markov chain. So this equation that is derived for a deterministic Boolean network has got a stochastic counterpart for a PBN. So to arrive at this counterpart, all right, we are going to have, let Wk is going to denote the probability distribution vector for a PBN at time k. That means you have 2 to the power of n states. Each state will have a certain probability, right, associated with it. So the ith component of this vector is going to be the probability that z at time k is equal to I. Okay, so everything has to sum up to 1, right? Then you can show quite easily that Wk is going to evolve according to this equation, right? When now A is a stochastic matrix of transition probabilities, right? All the rows have to sum up to 1, right? And this and if you take a look at the PBN paper, he has all the details, like all the bookkeeping necessary. I mean, here I'm just giving you the big picture, right? If you want to, maybe you don't need to because you guys are strong in this area, but if you need to go through that exercise, you can. It's all worked out in the paper, right? So this completes our limited discussion of PBNs as Markov chains. As with the majority of the literature, in this section we have focused only on binary quantization. We have talked only about zeros and ones, okay? But most of the theory and applications will carry over to any finite quantization in a fairly obvious fashion. Like you can have ternary, 1, 0, minus 1 and so on, okay? And it is in the ternary setting that we will consider the application of external control in the next chapter, okay? And the ternary setting is quite natural because we know that when you analyze microarray data, if you're taking ratios, you're going to get either significantly higher than 1, ratio significantly lower than 1, or almost equal to 1. So the ternary setting comes up quite naturally if you're looking at ratios of gene expressions. Any questions? So now that we understand, or at least we think we understand, something about the genetic regulatory networks, all right, how, like that the PBN could be, also be represented as a Markov chain. Now we want to look at intervention, right? So first we will look at intervention by flipping the status of a single gene. You just force a particular gene, all right, let's say it is highly expressed, you force it down, okay, by using, if it's a protein, you can use an antibody, right? Or you can use RNA interference, okay, that's a technology because from DNA you go to RNA then to protein, okay? So when that RNA comes out, if you get the complementary RNA to bind to it, there will be no translation, right? So that is called RNA interference, okay? That's another technique that is used quite commonly for, blocking the activity of a gene, right? So recognizing that a key goal of PBN modeling is the discovery of possible intervention targets or genes by which the network can be persuaded to transition into a desired state or set of states. In this section, we consider the effects of intervention by deliberately affecting a particular gene in an instantaneously random PBN, right? So whereas in the case of Boolean networks, attractors are hypothesized to correspond to functional cellular states, in PBNs, this role is played by irreducible subchains. Like if you look at the states, okay, because this is, if it's PBN, the transition between states is deterministic. Okay, so if you have n genes, you have a, I'm sorry, not PBN. If it's a Boolean network, the transition is deterministic. If you have n genes, you have 2 to the power of n states. Okay, and then you will say that if you are in this state, you will go with probability 1 to the next state, right? Whatever it is, right? In the case of the PBN, it'll be, you'll go with some probability, right, to some state, some other probability to some other state, and then all the probabilities will sum up to 1. Okay. Now, if you analyze like a state transition diagram like that, okay, you will see that there could be there could be chains like this where if you get in somewhere, you just stay in there. Okay, there could be disconnected components of the Markov chain. Okay, they are called irreducible subchains. Right. Now, if all the states communicate, right? If all the states communicate, then you say that the Markov chain is. Yeah, go ahead. You were going to say something. If all the states communicate, then you say that the Markov chain is ergodic. Okay. That means every state is visited, and you don't have any irreducible subchains. Okay. So absent the possibility of perturbation, that is p equal to 0, right? Remember p, not right here, but sometime back we said that p was the probability, right? That a gene will randomly change its value, okay, from 0 to 1, okay? So if the probability for that is 0, then all states will not communicate, right? So if absent the possibility of perturbation, a PBN is unable to escape from an irreducible subchain, right? It's just like the basin of attraction, right? In the case of the Boolean network, if you get in there, that's where you have to stay, okay? You cannot go anywhere else, all right? And implying that the cellular state cannot be altered. If on the other hand, p can be a small number, p is a small positive number, then the Markov chain becomes ergodic, right? Because you can go from any state to any other state. The probability is, it might be highly improbable that you will visit certain states, but still there is a non-zero probability, right? So if p is positive, then the Markov chain becomes ergodic, and there is a chance that the current cellular state may switch to another cellular state by means of a random gene perturbation. So that's how you get all the states to communicate. Now, this business of putting in a P is positive. We are attempting to justify that, saying the Markov chain will become ergodic, the gene might flip and all that. But the biologists, they prefer the ones where it doesn't flip, because if you get into apoptosis or cell proliferation, you will stay there. Okay, you're not going to get out of there, right? So this is something, an assumption that is made to make the mathematics go smoothly, right? And you can kind of justify it. Yeah, there is a perturbation, it might flip and all that. But from the biological point of view, the biologists would be more interested in the theory where it is not ergodic. So let's say we have these irreducible subchains, okay, and something got stuck in a bad subchain, right? You want to get it out of there, okay? And let's say you have a number of genes that you can intervene with, okay? You can change some genes from 1 to 0, right, or 0 to 1, and there are a number of them. The question becomes, which one are you going to use, right? Which one are you going to use to maximize your chances of getting out of that bad state, right? So flipping the values of certain genes is more likely to achieve the desired result than flipping the values of some other genes. So our goal is to discover which genes are the best potential lever points in the sense of having the greatest possible impact on desired network behavior, so that we can intervene with them by changing their value 1 or 0 as needed. In addition, right, if you're doing cancer treatment, you don't want to apply all kinds of drugs, okay, because then the cancer will get cured, but the patient will be dead, okay. So, right, I mean, you don't want to do that. So, because these drugs have toxicity, right? They're toxic, so, and they have side effects. So in addition, you wish to be able to intervene with as few genes as possible in order to achieve your goals, right? So to motivate this discussion, we will illustrate the idea with an example, and that's an idea that is taken from, that's an example that is taken from that paper, the original PBN paper. But I think it's a nice example, right? And it'll clarify a lot of things about PBNs, okay? So suppose you're given a PBN that consists of 3 genes, X1, X2, X3. Okay, so this is a toy example, okay, not a real world example, all right? And let's say for the first gene, all right, you have 2 predictors associated with it. For the second gene, you have only 1 predictor, and then you have 2 predictors associated with the third gene, right? And let's say the truth table is as follows, as shown on the following picture. This is the truth table, okay, for the PBN. So this is X1, X2, and X3, all right? So you have, each of them is binary, all right, 0, 1. So you have a total of 2 to the power of 3, 8 possible states, okay? So if you are in this state, okay, then you will transition, right? So the first state will transition according to the first predictor, second state according to the second predictor, and the third state according to the third predictor, right? But then even, for the first gene, all right, it has 2 predictors. And see, the probability adds up to 1. So so the first gene will always transition with a probability of 0.6 according to this first predictor, the truth table of which is given here, all right? And it will transition with a probability of 0.4 according to this second predictor that's given here, okay? Same thing for gene number 2, you have only 1 predictor, so that's why the probability is 1, right? So gene number 2, if it's 0, 0, 0 at the next time step, gene number 2 will be 0, right? 0, 0, 1, next time step, gene number 2 will be 1, okay, with 100% certainty. So that's why this is 1, right? And similarly for gene number 3, you have again 2 predictors, okay, and the probabilities must sum up to 1. Both of them are equally likely, so if you are in 0, 0, 0, at the next time step, gene number 3 is going to be 0, right? But there will be cases where it will be different, okay? If it's 0, 1, 1, if you are evolving according to the first predictor for gene number 3, at the next time step it will be 1. If it's according to the second predictor of gene number 3, the next time step it will be 0, right? So this is the truth table that is describing the PBN, okay? And you can get the dynamics from here, because you know if it's 0, 0, 0, you can figure out with what probabilities it is going to transition to which states, okay? And so here you have some choices, because there are 2 possible predictors here, okay? So you have a total of 4 networks, right, that you can use, right, that you can get, all right? The first network will correspond to this one, all right? Then the predictor for gene number 2 and one of the predictors for gene number 3. So there are 4 possibilities here, right? So the truth table results in 4 possible Boolean networks, and these are the predictors that are given here, okay? So the first predictor for gene number 1, first predictor for gene number, the only predictor for gene number 2, the first predictor for gene number 3, and so on, okay? And you can calculate the probabilities also, because if it's like first predictor for gene number 1, first predictor for the only predictor for gene number 2, and the first predictor for gene number 3, you can go back to the table, assuming that the selections are independent, all right? So it's going to be 0.6, all right, times 0.5, okay, that will give you 0.3, right? So you can go ahead and do those calculations, right? It's not a problem, right? Now, having done all these calculations, you'll be able to come up with the state diagram of the Markov chain, because there are 8 states here: 0, 0, 0, 0, 0, 1, 0, 1, 0, so on up to 1, 1, 1. Okay, and you will have probabilities of transitions between the different states. Okay, so starting from this diagram, and again in that paper it's all worked out, right? It's not that difficult. If you want to, you can go through that exercise, right? But I'm assuming that you have had sufficient exposure to stochastic processes. You know how to do this stuff. So you will come up with that transition diagram that is shown here, right? You come up with this transition diagram, right? With all these different probabilities, right, that are coming from the selection probabilities for the individual networks, right? So like you see, you have 1, 1, 1. If you go to 1, 1, 1, okay, you are stuck there. You ain't getting out, right? It's with a probability of 1, you will continue. So this is what is called an absorbing state. Once you get there, you don't get out, okay? Similarly, 0, 0, 0, right? This is also an absorbing state. Once you get there, you don't get out, right? Now, it may so happen that in a therapeutic situation, this might be a good state and that's a bad state, okay? So you want to get out of there, okay? So how should you get out of there? You want to intervene with one of these genes, okay? Let's say you will make the first one 0, okay? And then see, okay, is that increasing? So if you make the first gene 0, you will end up here, right? If you make the second gene 0, you'll get 1, 0, 1. You'll end up here. If you make the third gene 0, you'll end up over there. Okay. So the question is, which of these should you do, right, to maximize your chances of, let's say, getting out of this bad state and getting here, right? That's the idea, at least in this chapter, right? So as I said, suppose that you're currently in state 1, 1, 1, and let's say that corresponds to cancer, right? And you wish to eventually transition to state 0, 0, 0, right? And the question is, with which one of the 3 genes, X1, X2, X3, should you intervene such that the probability is greater that we'll end up in 0, 0, 0, right? All right, any questions? So your objective is basically to reach 0, 0, 0 starting from state 1, 1, 1. So which gene should be flipped, right? And this stuff is actually worked out in this paper, right? Yeah, go ahead.
When you say we have an
Absorbing state, yeah.
absorbing state there, what's the situation that we stay there? I mean,
Yeah, absorbing state means once you get there, okay? See, this is P1 plus P3 with the probability you got in there. Once you got in there, the probability of transitioning to itself is 1, okay? So once you got in there, you don't get out, right? You will, if you allowed a network with perturbation, right, you will not have an absorbing state, because there will be a small probability of getting out of here to every other state. But if you don't allow perturbation, you will have some absorbing states. Like once you get in there, that's it, okay? You are going to stay there. This is like the attractors of a Boolean network, correct? If you get into that basin, you will get there, okay? Here this is called an absorbing state. Similarly, this is also an absorbing state, because once you get into 0, 0, 0, with a probability of 1, you're just going to stay there, okay? Unless somebody kicks you out of there, or something flips or something happens, you're just going to stay there. Yeah.
so to change to other states, we have to consider this perturbation.
Yeah, you have to perturb one of the genes. Okay. If you put in like 0, 1, 1, you will go here and you will start again. Okay. If you put in 1, 0, 1, you will go here and start again. If you put in 1, 1, 0, you will go here and start again. Okay. And the question is, which one should it be? All right. That's what I'm trying to answer.
And this would be considered as resetting the initial state? Or
Yes. This is resetting the initial state, because you did not change the wiring in the network, correct? The diagram in the network, it is just the initial condition. You move from here to here or here or here. Okay. Yeah. Yeah. Good question. Yeah. So if you flip gene 1, right? So you had 1, 1, 1. You made that 0, 1, 1. You end up here, right? Then you try flipping gene 2, right? That gets you in there, right? And then you try flipping gene 3. That gets you to 1, 1, 0, right? Now, if you look at this, okay, which one should you use, right? You can see that if you get in here, okay, or you get in here, right, which is what you would have got, which is where you would have gone if you flip gene number 2 or 3, you ain't getting out of there, because everything is going inside, you see? inside this class, all right? So there's no hope of getting out there. Ultimately, you will end up in that absorbing state. You'll do all kinds of things, and finally you'll end up here and you'll stay there forever after, right? So in this example, it's relatively easy to see that you should be flipping gene number 1, right? The first one, because then you're out of here. At least you have some chance of going there. Okay, it's not guaranteed. It's not guaranteed because if you make the switch from here, then again you're going to get stuck. But at least to have some chance of getting out of the bad state, you have to work with gene number 1. Okay, and in this example, it's easy to see. Right? The question is, in a more general situation, okay, can we have a formal method to figure out which gene to intervene with? Okay, and the answer is yes. Now assume that there is independent, we didn't have that here, okay, but suppose, so we didn't have that here, like we didn't have random gene perturbation, otherwise all the states would communicate with each other, okay, from every state you can go to every other state, maybe with different probabilities, but, or with small probabilities. Now let's go ahead and introduce random perturbation. So assume that there is independent random perturbation with p greater than 0, so that the Markov chain becomes ergodic and every state will eventually be visited. So from every state you can go to every other state. The question of intervention could be posed in the sense of reaching a desired state as soon as possible, as quickly as possible. Right? For instance, in example 1, the example that we just finished, if p is very small and we are in state 111, then it will be a long time until we reach 000, right? Because that perturbation probability is probably very small. And if you set x1 equal to 0, you're much more likely to get there faster. Okay? Because because if you look at that diagram, right? If you look at that diagram, if you're in 111, right? Even if there's a small probability of perturbation, right? You'll have to go over here. You have to cross all these other states and go. But if you put in 011, you probably have larger probabilities that are leading in there. So hence, we are interested in the probability fk of xy that starting in state x, the first time the PBN will reach some given state y will be at time k. Right? You're interested in this probability. This is known as the first passage time from state x to state y. Okay, how many time steps is it going to take to go from state x to state y? Right? So if k is 1, right, then fk of xy is basically axy, which is just the transition probability from x to y. Okay, that's from the original network. Right? K is 2, you have to do some calculations, okay, but it can be done. Right? So for k greater than equal to 2, you can show that you can calculate fkxy like this. Okay, basically it will be the transition. So going from x to z and then going from z to y. Right, x to z in one time step and then from z to y in k minus 1 time steps. Right, so it's not hard to see that this is going to hold. Right. Now we can examine our results by considering the following quantity. Okay, so we are asking about going from x to y in one time step. That's corresponding to k equal to 1. Right. What is the probability of going from x to y in 2 time steps? That will correspond to k equal to 2. Right. What is the probability of going from x to y in k0 time steps? 1, 2, 3 up to k0. Okay, that's just the sum of these because these are again mutually exclusive events. Right. And you guys are experts in stochastic processes, or at least I think so. Right. So you have no problem with that. Okay. So this will be the probability that the network starting in state x will visit state y before time k0, right? So as a special case, when k0 is infinity, hk0xy is the probability that the chain ever visits state y starting at state x, which is actually equal to 1 because we have made the Markov chain ergodic. Okay, you can go from every state to every other state, right? Now, so this is one quantity that we will look at. So we would like to maximize this quantity, okay? Like we want to go from x to y and there are different possibilities for x because if I flip one of the genes, okay, I will get different possibilities for x. For each of those guys, I will calculate, all right, what this total quantity is. I'll fix some number, k0 is 20 or 100 or whatever. I would like to maximize this probability, right, of going from this state to the destination, let's say in 20 time steps or 100 time steps. Right? I want to maximize that probability. That's one approach. The other approach is to work with what are called mean first passage times. Okay, we talked about the first passage time. Okay, so that's the number of time steps it will take you for you to get from x to y, right, for the first time. Okay, So now that is a random variable, right? I mean, because here things are evolving in a stochastic fashion, all right? So you will take the mean, all right? So k is the value of the first passage time, multiply that by the probability, right? That will go from x to y in k time steps, and then sum that up. Okay, this is the good old formula for calculating the mean of a discrete random variable, and this is called the mean first passage time, right? Mxy, mean first passage time from state x to state y, right? So mxy is the average time it will take to get from state x to state y. Okay, and you would like to minimize, and here you would like to minimize the mean first passage time, right? Y is fixed, the destination is fixed. I'm going to flip one gene in X, all right, and I will get different states. Okay, which one is going to give me the minimum mean first passage time? Okay, that's the question that we are going to ask ourselves. So we can continue with that earlier example. So we put in in the beginning, every state was not communicating with every other state. We put in a small perturbation, right, p equal to 0.01, and now we have a steady state distribution, right? Every state communicates with every other state. The Markov chain is ergodic, so it has a steady state distribution, right? If it gets in there, once the distribution looks like that, the probabilities in each of the states is not going to change, right? And you can do the math and you calculate the steady state distribution like this, right? So there are 8 states, so these have different weights, right? You can see that the leftmost element will correspond to 0, 0, 0, rightmost to 1, 1, 1. So you can see that the PBN is spending most of its time in that really bad state, like 0.7310, right? So you don't want that, okay? So let our starting state be 1, 1, 1, and the destination state y be 0, 0, 0, because we are saying that that's the good state, okay? So the question is, should I intervene with gene x1, x2, or x3? Okay, so I have 1, 1, 1. Should I make the first one 0, second one 0, the third one 0? Right? So using first passage time, you can compute this quantity. Okay, so if you intervene with the first one, you will have to go from 0, 1, 1 to 0, 0, 0. If you intervene with the second one, you'll have to go from 1, 0, 1 to 0, 0, 0. Intervene with the third one, you will have to go from 1, 1, 0 to 0, 0, 0. Right? So you can go ahead and compute this quantity, right? And you can add this up. Let's say you decide that over 20 time steps you're going to add it up. You add up all these probabilities, okay? And so for the 3 states of interest, namely 0, 1, 1, 1, 0, 1, and 1, 1, 0, and the plot is given. So you can do the computations, right? Do it on the computer, run your simulation, and the plot looks like this, right? So you have, this is what the sum of the probabilities look like. If you flip the middle one, it's 1, 0, 1, flip the last one, it's this line, and if you flip the first one, it's this line, okay? So which one should you intervene with? First one, yeah, because that one you can see that in 20 time steps is almost 0.25, okay, whereas these guys are still struggling with 0.05, right? So what we saw in that picture, just by hand waving, it can be rationalized by using more mathematical arguments, right? And even if you do it first passage times also, you will come up with the same conclusion, right? So the plots indicate that starting at state 0, 1, 1, the network is much more likely to enter state 0, 0, 0 sooner than by starting at states 1, 1, 0 or 1, 0, 1. For instance, during the first 20 steps, there is almost a 0.25 probability of entering 0, 0, 0 starting at 0, 1, 1. Whereas starting at 1, 1, 0, 1, 0, 1, there is only a 0.05 probability. Thus, we should intervene with gene x1 rather than with x2 or x3. Right? Now, were we to base our intervention on mean first passage time, then the best gene for intervention would be the one possessing the smallest mean first passage time to the destination state. And for this example, you can go and do the calculation. Okay, I mean, you'd have, of course, know how to do the, you'd need to know how to do the calculation for the mean first passage times, but don't worry, people have figured those out 40, 50 years ago, right? So you just have to go and apply, right? So the mean first passage times corresponding to the perturbations of genes x1, x2, x3 are these numbers. Okay, so many seconds. So since the first one is the smallest, this again supports the conclusion that gene x1 is the best candidate for intervention. All right, any questions?
Is this always growing?
This is always what?
This function is always growing?
Which function?
The ones you showed before?
Yeah. That will increase, yeah.
Always increase?
Yeah, that will increase, yeah. With time, because you're adding, because you're taking the probability of a larger set, okay? So yeah, it will increase. Yeah. So to sum, yeah.
Just go over the diagram again.
Which one? This one?
This one, yeah.
Yeah.
How you conclude
No, yeah, see, what this is telling you is that this is telling you for each time, okay? It is telling you the probability that you will go from that one state to the other, right? In 20 time steps. Okay, so if you look at 20, it's telling you the probability of going from that origin to the destination, right, in 20 time steps. Okay, what is the probability, right? 20 or less. Okay, so you can see that for this guy, if you change your source to or your origin to 0, 1, 1, this probability is the highest. Okay, it's 0.25. Whereas for these guys, even if you allow 20 time steps, these are staying pretty low, right? Yeah, you're just adding together the probabilities, okay? Because these are disjoint ones. You reach in one time step, reach in two time steps, three time steps, and so on. So you're adding the probabilities together. All right. Any other questions? So to summarize the results of this section, given an initial state, we generate different states basically by perturbing one of the genes. Okay. So this is the whatever 2's complement sum with a basis vector, right? Ith basis vector. So where EI is the unit binary vector with a 1 in the ith coordinate by perturbing each of the n genes. And then you compute this quantity hk0 xi, that's the new origin to the destination, and some constant k0. Let's say you say 20 times steps or 100 or whatever you want. Okay. Then the best gene for intervention is the one for which this quantity is going to be maximum. That is given a fixed k0, the optimal gene xi-opt satisfies this. Okay. Now, if you change k0, it's possible that in some example the optimum gene might change. I don't know. I haven't worked it out. Okay. But from this example, it looks like it would probably stay the same. Right? The alternative would be to minimize the mean first passage times. The optimal gene would satisfy the gene which the argument which minimizes this mean first passage time. Okay. All right. So now we look, but this kind of intervention, it's a one-time thing. It's like resetting the initial condition. Okay, it's not going to alter the steady state behavior. So if you are saying that in cancer the steady state behavior is indicative of the phenotype, right? Then you need to do something more, right? So the type of intervention described can be useful for modulating the dynamics of the network, but it does not alter the underlying network structure. Accordingly, the stationary distribution will remain unchanged. However, an imbalance between certain sets of states can be caused by mutations of the wiring of certain genes, thereby permanently altering the state transition structure and consequently the long-run behavior of the network. So we are interested in developing a methodology for altering the steady state probabilities of certain states or sets of states with minimal modifications to the rule-based structure. Remember, we had the truth table, okay? So now we are going to, let me just explain what we are going to do, okay? And then I come back here, it will be a lot easier to go through this text. Yeah, you have this truth table, all right? So what you're going to do is, you are going to go and change, let's say, one of the predictors, okay? Like see here, the truth table has 0, 1, 1, 1, 0, 1, 1, 1, right? So there are how many possibilities here, right? This location you can have either 0 or 1. This location 0 or 1, okay? So you have 2 to the power of 8 possibilities, possible predictors, out of which this one has been chosen, okay? So 2 to the power of 8 is 256, okay? So what you're going to do here is that you are going to go and change these guys, okay, and then calculate the steady state distribution, okay? So there are 5 predictors here, right? You can change like so 256 in each case, so there are 256 times 5, that many possibilities, okay? You're going to change the network in that many ways, okay? In each case you're going to go and look at the steady state distribution because you want to see how the steady state distribution. So this is a brute force search procedure. You don't like the weightings. Remember, 111 had a weighting of 73%, right? 000 had a weighting of 7% or something when we did the calculation with perturbation, right? In that example. So let's say I don't like that, okay? I want both of them to be weighted 40% each, let's say, right? So then the question becomes, if I'm allowed to change only one predictor, which one should I change and how, okay? And it's not a neat way, they just do a brute force optimization search procedure, okay? They'll make the change, then they'll calculate, right? And then see which one is located closest to the target, right? That's what is going to happen. So just keep this table in mind, it'll make it a lot easier to go through that text. So however, an imbalance between certain sets of states can be caused by mutations of the wiring of certain genes, thereby permanently altering the state transition structure and consequently the long-run behavior of the network. So we want to develop a methodology for altering the steady state probabilities of certain states or sets of states with minimal modifications to the rule-based structure. Again, you don't want to use too many drugs, okay, so minimal modification. So the motivation is that these states may represent different phenotypes of cellular functional states, such as cell invasion and quiescence, and we would like to decrease the probability that the whole network will end up in an undesirable set of states and increase the probability that it will end up in a desirable set of states. So one way to accomplish this is by altering some of the Boolean functions in the PBN, so the truth table will get changed. An additional goal is to alter as few functions as possible. You don't want to alter too many of those predictors, okay? So formal methods and algorithms have been developed for addressing such a problem. Here we briefly discuss the results. So consider an instantaneously random PBN with perturbation and two sets of states that you are interested in, AB, that are in the state space, 0, 1 to the power of n. So since the Markov chain is ergodic, by putting in a perturbation we made it ergodic. Each state has got a positive stationary probability, right? And thus we can define for any set A of states, the stationary probability associated with that set is basically the sum of the probabilities of the elements that make up that set, right? And similarly, you can define pi b. So suppose we are interested in altering the stationary probabilities of these two sets of states in such a way that the stationary probability of A is decreased, right? Maybe that's a bad state, we want to decrease it, and the stationary probability of B is increased by lambda, right? Where lambda is something between 0 and 1, right? We want to alter the stationary probabilities. So as already mentioned before, these two states may represent two different cellular functional states or phenotypes. So in order to achieve this, suppose we alter the jth predictor corresponding to the ith gene, right? The entries in that truth table, the columns in that truth table, okay? By replacing it with a new function, right? And of course, the probabilities still have to match up, okay? If you change this, okay, you have to make sure that even if you change the probabilities corresponding to the individual predictors, that still has to sum up to 1, okay? So then you'll have a new PBN whose stationary distribution we can denote by mu, and letting mu A and mu B be the stationary probabilities of A and B under the altered PBN model, where you have changed one of the entries in the truth table, one of the columns, all right? We pose the following optimization problem, all right? So given sets A and B, predictor functions Fij together with their selection probability Cij, whatever information is given in that truth table, okay? And lambda belonging to 0, 1, select I0 and J0, okay? That means select the predictor, all right? Which predictor corresponding to which gene you are going to change, okay? Which column, all right? And a function Gi0, J0. And how are you going to change that particular column to replace this such that the sum norm of the difference between pi a minus lambda, right? We are trying to decrease a by the probability mass in a by lambda, right? And you're trying to make it equal to mu a, okay? So that should be small, and even this one should be small. They're minimum among all possible, changes that are allowed. All possible predictor changes. That 256 times whatever 5, right? So an additional constraint could be that Gi0, J0 has no more essential variables than Fi0, J0, right? Because in the truth table, essential variables are variables that really matter, okay, when you're doing the prediction. So here we are allowing only the alteration of one predictor function. More generally, you could pre-select a number of predictor functions that we are willing to alter, but then the number of cases will be a lot more, okay, right? So here it's 256 times 5. So for the PBN of example 1.1, the figure shows the state transition diagram, the figure that I showed you, assuming no perturbation p equal to 0. From the figure, we saw that there were two absorbing states, 0, 0, 0 and 1, 1, 1. Suppose 1, 1, 1 corresponds to cell invasion and rapid proliferation, and 0, 0, 0 corresponds to quiescence, right? So you want to go there, you want to go to 0, 0, 0. You don't want to stay in 1, 1, 1, okay? So now you get all the states to communicate by assuming a perturbation probability, small perturbation probability of 0.01. You can do an analysis, and you will see that the probability, stationary probability associated with state 0, 0, 0 is just like 7%, right? 7.5%, while the one associated with the bad state is like 73%, right? So thus in the long run, the network will be in quiescence only 7% of the time and will be in proliferation 70% of the time, right? You don't want that, okay? So suppose you want to alter this imbalance and require the stationary probabilities to be approximately 0.4 for both these states, right? And then in that case, if it's 0.4 for this, 0.4 for this, the other 6 states will be forced to share the remaining 0.2 of the probability mass. So in the framework of the optimization problem that we have already described, A will become just this single point 111, that state. B will be this. Probability associated with A is this, probability associated with B is this, and then the desired stationary probabilities associated with A and B are zero point 0.4, and lambda is 0.3279, right? And finally, suppose we are allowed to change only one predictor. In the truth table of that example, this corresponds to changing only one column while keeping the selection probabilities unchanged, right? Thus, there are 5 possible columns and 256 possibilities for each. So there are 1280 possible alterations, right? So you generate those and calculate the stationary probabilities for these two states for each one of them, right? And you get a plot like this, right? So you make all these changes, right? This is what the diagram looks like. Yeah, yeah.
It shouldn't be to 56 to the power of 5 possible alterations.
Why is it going to be to the power? No, you are allowed only one, okay? You're not allowed to change many columns, any one column, okay?
Okay.
Yeah. Yeah, if you're allowed to do all 5, then it'll be, yeah.
Okay.
Yeah. So if you look at this figure, right, you want it close. So these are the probabilities, right, mu of 0, 0, 0, stationary mass in 0, 0, 0, okay, after the change, stationary mass in 1, 1, 1 after the change, okay, and you're interested in making both of them 0 0.4, 0 0.4, so it's one of these, okay, and these correspond, this color coding is, if you change the predictor number 1 for gene number 1, that's this color, 2 for gene number 1, this color, and so on, okay. So you can see, I mean, there are all these 1280 things that are plotted here, okay? And the brute force search procedure, you look in here, and this is the predictor that will do the job, okay? But you can see that there is some, structure in the space, okay? So maybe instead of doing a brute force optimization, you could probably use something like genetic algorithms or something like that to cut down on the time. That's what they did on the paper. But again, no deep theory, okay? It is basically a brute force search, right? Make all possible changes and then see the result and then pick the best one, right? So the optimal values for the error function are indicated by an arrow in the figure. That's the 0.4, 0.4, right? The objective function to be minimized is mu 0, 0 minus 0.4 plus mu 1, 1 minus 0.4. And this is the figure that you get. And the colors of the circles represent which predictor is altered. I already mentioned that. For example, red denotes the predictor F1, the first predictor for gene number 1 is altered. The optimal predictor is the one that alters the second predictor for gene number 1, right? Column 2 in the truth tables. And the truth table of the optimal predictor is this. Okay, you know that because you've gone through the computation. Okay, you know which one it is, right? And this predictor achieves the stationary probabilities for 0, 0, 0 is 0.4068, the other one is 0.4128. That's close enough. And the structure of the plot in the figure reveals an interesting phenomenon. The two stationary probabilities exhibit regularities forming clusters of points arranged in a linear fashion with different directions. In fact, this phenomenon has been observed in numerous examples. It appears that the alterations of different predictors tend to occupy different parts of the space, implying that for a given predictor there is a certain range of action which could be achieved by manipulating it, right? So based on that, you would like to use some genetic algorithm. So this suggests that a brute force search for the optimal predictor alteration may possibly be avoided by following a number of search directions simultaneously, with the more promising ones being explored further. And this in turn suggests the use of genetic algorithms for optimization. So in fact, genetic algorithms have been used to solve the optimal structural intervention problem posed here, and the resulting savings and computational effort have been remarkable. This is one paper, okay, that is there on the website, so you can take a look, right? I mean, yeah, you'd have to look at 1280 cases. Maybe they did like, I don't know, 20 or 30 cases and got the result. But again, I mean, it doesn't prove anything, right? So nonetheless, this remains an essentially brute force procedure, and better approaches need to be developed. Okay. So the next topic, which I will start on Wednesday, will be external intervention based on optimal control theory. Right. That's the next chapter. So we are getting close to the end, right? I mean, I'm on what? Yeah, we are getting close to the end. I need, I think about 4 people have contacted me with papers, and I told them that it's okay for them to present. I don't know, are you guys ready? I mean, I know Shabnam, you contacted me, right? Are you ready to start presenting next Monday or what? Okay. I don't know then how we do it. You have to come up with creative ideas, because I think by this Friday I will run out of material to lecture on, okay? And we need to finish these presentations before the end of the semester. So to figure out, that's also another, assignment problem for you guys, okay? Right? I mean, optimization. I think some people are probably ready, right? I mean, all right, all the people who have selected papers, let me know, okay? If nobody is ready, I don't know how to do it, okay? I mean, at least during the regular class time, right?